And we're back. So this is now talking about 6.2 and 6.3, the next two topics in your Line It Yourself section. So this is going to be a little bit of recap of energy diagrams, which we talk about in Unit 5, as well as heat transfer and thermal equilibrium. This is all going to be conceptual, although I can throw in some numbers. In the next class, when we meet back in person, we'll be doing the thermomath stuff proper. So we've already talked about exothermic reactions and endothermic reactions in the context of these reaction profile diagrams that we looked at in kinetics. So again, just recall that we are looking at the difference in where the products are from where the reactants are. The activation energy is certainly something that affects kinetics, right? And we talked a lot about that intermediate area when we looked at reactions in the context of kinetics. But when we look at thermodynamics and things like, is this endothermic or exothermic, we're really looking at the end state and the starting state, right? Where are the products and where are the reactants? And sometimes you'll hear the term enthalpy referred to as a state function. Enthalpy is a state function. And state functions are properties that don't depend on the path taken to get there. So kinetics, a lot of the stuff we talked about is, how can I add a catalyst and make the activation energy smaller? The endpoint is still going to be the same, right? I still started over here and I still ended over here. So the enthalpy change, meaning products minus reactants, getting that value for delta H, is a state function because it's the same regardless of if I used a catalyst or if I didn't. The activation energy was very small or very large. So again, when we're talking about exo and endothermic, we want to think about the system relation to the surroundings. So our system is losing energy when exothermic reactions. That's why delta H is negative for exothermic reactions. And we see this because the products have less energy than the reactants do. Endothermic is just the opposite. We have to add overall energy into the system from the surroundings. So delta H for these guys is going to be a positive value. And yeah. So when we are talking about that delta H, again, that change in enthalpy, we are going to be referring to that as the enthalpy of a reaction. And I showed you guys a little bit in the last set of slides that sometimes you see a different subscript like solution or fusion or, combustion, whatever it is. Ultimately, those are all kinds of reactions, right? So delta H subscript reaction is our general idea of how enthalpy changes from the products to the reactants. Now, you see this sigma here. If you're not familiar with that notation, that means the sum of. And we see it again here for the reactants. So that's all sigma means. And then we see this delta H subscript F, delta H subscript F with a circle. We are going to talk about the F and the circle a little bit later. So for now, don't worry about them. What I do want to emphasize is that we are summing the products enthalpy states and then subtracting the reactants enthalpy states, okay? And then lastly, this delta H of reaction is measured in kilojoules per mole of reaction. So we assume that an entire reaction is 1 mole. For example, if I take, what is something good like creation of HCl from its constituent elements, right? Let's just say hydrogen and chlorine gas combined make HCl. Let's say delta H for this is, I don't know, negative 200 kilojoules per mole of reaction. Well, if I have 1 mole of HCl produced, right, the reaction says there's 2 moles of HCl produced. So if I have 1 mole, and I'll do a quick conversion, 1 mole HCl produced, how much heat would be released? Well, I would say, hey, there's 2 moles of HCl for every 1 mole of reaction. And I'm told by this delta H value that for every 1 mole of the reaction, I release 200 kilojoules of energy. So if I'm only producing 1 mole of HCl, that's going to be 200 divided by 2, 100 kilojoules released. Right. So again, we'll fiddle with this sort of stoichiometry with molar reaction a little bit later when we start doing more quantitative stuff. But I just wanted to showcase that here, so we're used to that notation, moles of reaction. So we talked about activation energy and kinetics a lot, but again, what that is this in-between state where we are breaking the bonds of all of our reactants or overcoming IMFs, and we're starting to form these new bonds, new intermolecular forces between product particles. And ultimately, if that difference is negative between where we start and where we end, we get something exothermic. And if it is positive, we get something endothermic. But again, to get through to the products, I have to start breaking some stuff apart, and that requires energy. Even if overall this is exothermic, I have to jump over a hill in any reaction. And oh my gosh, that's the reaction I just made up. That's so cute, and it is exothermic. Oh my gosh, I'm so smart, you guys. I already talked about catalysts. I already talked about that. Delta H hasn't changed, blah, blah, blah. Okay, Maxwell-Boltzmann curves. We spent a good amount of time looking at these in Unit 5, but they can show up in thermo for sure, especially when we're talking about temperature of different samples. So when you've got something with a higher temperature, it's going to be shifted to the right, and it's going to be shifted down a little bit. And if you've taken any calculus, this might make sense to you. If you haven't, don't worry about it. But basically, the idea is if you have the same sample, so same number of particles, the area, and you're changing its temperature, the area under the curve of this cold sample, right, this low temperature one, that area under the curve should be the same as the area under the curve for this warmer sample, because they are showing the same number of particles. It's the same sample, I just heated it up, right? So as I shift to the right, I also need to squat it down because my y-axis really just tells me how many particles have that energy, right? This is really just like frequency. You could think of it like that, a frequency y-axis, where the x-axis is how fast are they moving, right? How much kinetic energy did they have? And I mentioned this in the previous video, but kinetic energy is related to mass linearly and velocity exponentially squared. Okay, particle diagrams. This is, I promise, like the easiest particle diagram you'll ever do. I really wanted to mention this because the 2024 FRQ last year had this stupidly easy question, and it just boggled my mind that they bothered asking it, but here it is. When you're trying to show on a particle diagram relative kinetic energy, you draw a bigger arrow to show it's moving faster with more kinetic energy at a higher temperature, right? So here's 100 C, here's 500 C. Oh my gosh, it's crazy. But do pay attention to the fact that the temperature is an average, so not all of these particles have the same size arrow, right? Some of them are kind of small, some of them are a little bigger. Even in the warmer sample, right? This guy right here is kind of small, but the average of these arrows, just like the average kinetic energy of them, is definitely higher than what we see in the 100 degrees C. So let's look at that FRQ because it was hilarious. The prompt was putting a metal cube at 100 degrees C into a cup of water at 25 degrees C. And they wanted us to look at before, here are the water molecules in the cup, before you've added the metal cube. And then after, right, we've put this really hot metal cube in there. That's Spencer's cube. Yep, pretty awesome. We've put it into the cup, and because the metal is a higher temperature, it's going to pass energy into the water. So the particle should be moving faster. And all you had to do to earn this point was draw slightly bigger arrows on all these molecules. Can you believe that? Draw an arrow for each molecule to indicate how the speed of each of the molecules changes, right? So what do you need to know? Well, after the temperature of water would go up, right? So the kinetic energy go up. So bigger arrows. That's it, y'all. Stupid easy. Now, since that was on the FRQs last year, it's probably not going to be there this year, but might show up in multiple choice. I don't know. On the topic of mass, right, because we have this relationship right here, kinetic energy equals 1/2 mass velocity squared, we sometimes have multiple samples of gas at the same temperature. And this is a Maxwell-Boltzmann curve, right? So frequency of particles and then particle speed. We can see that this really heavy gas, xenon, has much slower moving particles, right? It's got heavier mass, so its velocities have to be lower if they're all going to have the same kinetic energy, right? And then we see by comparison, the one that's moving the fastest on average is going to be helium, right? Helium has a really small molar mass, 4 grams per mole, compared to xenon, which is like 130 grams per mole. So the helium, in order to have the same kinetic energy, right, their mass is so tiny, so their velocities have to be really big compared to the xenon, which is going to have really big mass, so it's going to have very slow moving speeds if they're all at the same temperature. All right, so really where the next topics are going to build off of is this idea of heat transfer and how we quantify it. So just a reminder that heat is going to flow from high temperatures to low temperatures. From high temp to low temp. And this is really just, again, about collisions, just like kinetics, like a hot particle and a cold particle bump into each other, there is some energy exchanged. And there's always this gradient where energy wants to heat up something that's at a little bit lower kinetic energy. So a couple different terms we use for that are pictured here. We're always going to have something that's hotter losing its energy and the colder thing gaining some energy, increasing in temperature. Seems pretty common sense, but needs to be said. Now, when we have two substances of different temperatures sit together for long enough, eventually they reach thermal equilibrium, and that just means they have the same temperature. Eventually. It might take a couple minutes, but eventually that will happen, right? Recall that temperature is average kinetic energy. So when we think about the energy transferred, once temperature has equalized between two objects that were originally different temperatures, once they've reached that same temperature, we can then do some calculations related to the actual energy that was transferred between them. So we'll get to that in our next class, but let's just look at some things qualitatively for now. So we've got this big old reaction here, and then we're given the delta H of the reaction. We're asked to draw a reaction pathway. So let's do that. We've got reaction progress on the x-axis and energy on the y. So this is exothermic, right? Negative sign on our delta H, and it's very exothermic, right? Negative 1100 kilojoules. So I'll draw my reactants here, go up some amount, and then I'm going to go like way down here for my products. And we're told to label the products, told to label the reactants, and to label delta H. So recall that delta H is this space right here, from the products to the reactants, from starting point to ending point in terms of their energy difference. Bada bing, bada boom. All right, and this one again is kind of setting us up for the next topics. So if we have 50 grams of aluminum, so this is our little aluminum block. Again, here goes Spencer, the geometry teacher, astounding you with his mastery of platonic solids. And it is at 85 degrees C, and we're going to put it into 100 grams of water. So here we've got a cup. Forgot I can sometimes draw straight lines if I just use my computer correctly. And the cup is full of water. The water is 25 degrees Celsius. and we've got 100 grams of it. Now we're also told these specific heat capacities for each substance. And we'll talk about that a little bit more in our next class, but basically this says how energy efficient is it to heat this thing up. So a low specific heat capacity means not much energy required to change temperature. If you have a high specific heat, like water's specific heat capacity is almost 5 times as big, then it will require a lot of energy to change temperature. And you know this if you've ever tried to boil water and it took like 15 minutes or more, the pan heated up real quick, that metal pan. But your water's temperature took a long time to change. Okay, so this question is really just asking about what happens to the aluminum, and we're specifically asked temperature, average kinetic energy, and average speed. Now, hopefully by now you can make the connection that all three of those things are directly related. So temperature, right? The initial temperature of the aluminum is higher than the water's, so aluminum's temperature is going to decrease. Because temperature is the average kinetic energy of a sample, kinetic energy has to decrease proportionally. Now we also know that kinetic energy is made up of 1/2 mass times velocity squared. So the velocity, I'll just write out that word so we don't get confused. Velocity is also going to decrease. Now you might specify here, it's going to decrease by a different factor because of that squared sign, but qualitatively, this is really all I'm looking for, that these three things are proportionally related. And you could say from the perspective of the water, right? If I hadn't asked about aluminum, well, water's temperature would increase. Water's kinetic energy would increase. Its velocity would increase, just like we see in this, really advanced APFRQ question right here, right? This is basically another version of this question. So heat transfer, thermal equilibrium, eventually the temperature of the metal will decrease until it meets the temperature increase of the water. Now we'll talk about how to quantify what that temperature will be in our next topic. But that is all for now. Thank you for watching. Have a swell rest of your day and do your homework.